We will go first over the main equation involved in this chapter before starting problems. So first, we will see what are the cutting conditions and what equations will be used in this case. So in cutting operations, relative motion is required between the tool and work to perform a machining operation. The primary motion is accomplished at a certain cutting speed v. In addition, the tool must be moved laterally across the work. This is a much slower motion called the feed F, and we can see the different variables here in the figure. So this is a cutting operation, it is the turning operation. As you can see, you have removal in three directions. And you have your work part is rotating, okay? So sometimes it depends on the case. Sometimes you can have relative motion of the part relative to the tool or the tool relative to the part. So it's not a problem. What we want is relative motion, and independently of what is moving, okay? So here, for example, let's say we are turning the work part, and this is the tool. And at the same time, we have that the tool is first, we put it at a certain depth into the work. So already we have removal in this direction. And we have motion of the tool in this direction, which is parallel to the axis of the work part. So this is the feed. The feed in general is given in millimeter per revolution, and you can convert it to millimeter per second. Okay. So each complete revolution of the work part, your tool will do a small translation, and the rate of translation can be calculated as the distance moved per revolution. Plus that you have your turning work part, let's say. So you have here a certain cutting speed. So you have removal in depth, you have removal parallel to the work part, and you have removal in the tangential direction. Okay? So in this case, the primary motion, as we said, is accomplished by the cutting speed v. And in addition, the tool must be moved in a lateral way across the work. So this will be a much slower motion called the feed. And the remaining dimension of the cut is the penetration of the cutting tool below the original work surface, which is the depth. So in overall, okay, the speed, the feed, and the depth of cut will define the cutting conditions, and they form three dimensions of the machining process. And therefore, in this case, the removal rate can be calculated as the cutting velocity v times the feed f times the depth t, depth of the cut. Okay, and in addition, we can say that this process, turning process, is a single point tool operation because you have one cutting face. Okay, you have seen maybe in the, if you have watched the recording, the PowerPoint, you have also, for example, in milling and drilling, you have several, not single point tool, several point tools. In this case, you have several faces that are doing cutting operations. Okay. So for the removal rate, the unit will be in millimeter cube per second. So it's a volumetric rate, and it will express what is the rate of metal removed during the operation. Now, always pay attention for units. Okay, so let's say if you want to express your removal rate in millimeter cube per second, make sure to have your velocity in millimeter per second. Your feed is we will take the value in millimeter, okay, just per revolution. Okay, this is why here we put just millimeter, because we will consider one for one revolution what is the rate that is removed, and we have the depth of the cut. Okay, so in this way we get the removal rate in a millimeter cube per second. And then this following figure will represent the cutting operation. We will see together that in order to model the cutting operation, we will use a 2D model. Okay, so here in this figure, you have the orthogonal cutting model. First, you have the three-dimensional process in this figure here, and you have the 2D model in figure B. Now, you can see here that why we can do the 2D analysis, because we will see that the width factor, okay, it will not affect the performance. So we can deal with it as a 2D operation. And then in the 2D operations, the main variables are first, you have, if you compare when you have the depth of your tool in your work part, you have a difference between the level where you have the tool and the work part level. This is called the value, the chip thickness, T0, which is prior to, so it's the thickness of the chip prior to the chip formation. Okay? And then once you have the operation, it's a cutting operation that is based on shear. So you have a plane of shear here. The shear plane is doing with your work part an angle of phi. This is called the shear angle phi. And we have also once you have, after cutting, you have formation of chip, the chip thickness, TC, which is calculated as the thickness that is perpendicular to the face of the tool. Okay, this is TC. And the angle between the plane of the tool, so here you have the plane, the cutting, you have the face of your tool. The angle between the face of your tool and the perpendicular to the work part is called rake angle alpha. And together we will see how to derive a relation between these parameters. Okay? So during cutting, the cutting edge of the tool is positioned at a certain distance below the original work surface. This corresponds to the thickness of the chip prior to chip formation, T0. And as the chip is formed along the shear plane, its thickness will increase to Tc. This is why an important parameter to define is the ratio of T0 to Tc. And this ratio is called the chip thickness ratio, or simply the chip ratio. And since Tc, which is the chip thickness after cutting, is always higher than T0, then T0 over Tc will be lower than 1. Now we will see that this orthogonal model, simplified in 2 dimensions, will be used for as analogy with the turning operation. Just to see the analogy before we continue, I want you to look at this figure. So here, if you compare the two models, okay? So in the case of the orthogonal cutting model, you don't have turning, and it's a simple operation. You have a tool moving at a certain velocity v, and you have the cutting force and the thrust force developed here. So, but you can do a certain analogy in the turning operation. Because look, if you do a comparison, first, you can consider that the feed F, okay, which corresponds here to, if you want, this is F, which is the thickness removed per revolution. Okay, for a complete turn, you will remove all of this. So this is your feed. In comparison with this figure, you can see that the feed F corresponds to the thickness of the chip before the cutting operation. So by analogy, if you want to extend the formulas used in the 2D model to the turning operation, then T0 will correspond in your turning operation to the feed F. Okay? Now, concerning the depth of your cut, D, here, will be, by analogy, the width W of your cut here. Because look, imagine that you, here you have a circle. مظبوط. It's a circular operation. إذا فتحناها, so if we open it, if we open the circle, we will obtain that the depth is equivalent to the width here. Okay? يعني إذا بنفتحها بيطلع عنا شيء هيك, والدي بيكون equivalent للwidth W. Okay? So in the equations, if we want to extrapolate the equations of the orthogonal model, cutting model to the turning operation, the equivalent to the depth will be the width of the cut. Now, for the cutting speed, here you have the cutting speed in this case is the velocity of the advancing tool, and here it will be the velocity of rotation v. Okay, and concerning the other parameters, the cutting force is the same. And in both you have a cutting force. Okay, and the cutting force here you can see FC, which is, if you want here, it is collinear with the cutting force is collinear with the velocity. So here at each step, at each cutting step, you have the at contact point you can draw the linear velocity. This will correspond to the direction of the cutting force, and you have the thrust force that will be perpendicular to the cutting force. Okay, so these are the main variables involved, and you can do analogy between the orthogonal cutting method and the turning operation. Okay, so now all the relations developed, if you want to extrapolate them to turning operation, all you have to do is to replace T0 by F, to replace omega by D. And for the other parameters, it's the same thing: cutting speed V, cutting force Fc, and feed force. Yeah, just you have the thrust force in orthogonal cutting is equivalent to the feed force in turning operation, because the feed force will be the one that is perpendicular to the cutting force. Okay. So now, if we go back to the formulas, so now we will develop formulas for the orthogonal model, and then we will extrapolate them to the case of turning. Okay. So to start with, we said that we will define the ratio T0 over Tc. Now we want to find the expression of this ratio. Okay. So we will try to find this ratio function of our angle. This is why I will take this figure and do a small analysis here. Do you see the paint file now?
Yes, doctor.
Okay. So my purpose is to determine T0 over Tc function of the angle. So if you look here in this figure, this is T0. Okay. So this is T0. And if we call this distance is called Ls, at the it is the length at the level of the shear plane. Okay. So considering that we will see that this length will be simplified in the ratio. But as you can see, you can say that T0 over Ls, okay, will correspond to what? This angle is phi. This is phi, okay? So you can write that sine phi. So the first equation we can write is that sine of angle phi is equal to T0 over Ls, the shear length. Okay, so we can replace in the ratio T0 by the shear length times sine phi. Now, concerning Tc, as we said, is the thickness of the chip after the cutting operation, and it is determined. Tc is determined as the length perpendicular to the tool face. Okay, the rake face. So this is Tc. This is Tc. Okay, and in order to determine, if you want, this is a perpendicular angle here. This is 90 degrees. Okay, in order to find a relation between Tc and the Ls, I need this angle. I will use another color. So I will need now this angle here to determine this angle. 1 second. Oh, I don't know what is happening. 1 minute. It's not using this tool. Okay. So I want to find this angle now, okay? Because if I will call this angle, if we call this angle, for example, let's say theta, okay? We can say that TC is LS cosine theta. So TC is LS cosine theta. But what is theta function of our angle? If we look at our figures by using the geometry of the figure, you have that this angle here, if I will take another color for you to see it better. So if I take this line here, okay, this line, the blue line, is doing with the green line an angle of phi because they are alternating angles. So this whole angle is phi, okay? And what I want is the difference between the whole angle and the small one. The small angle, I will put it in another color. So here, this is the small angle. So you can say that theta is the difference between phi, which is in blue, okay, and this angle here. And to get this angle, if you look well, you have the blue line is, this line is perpendicular to the vertical, okay? And we have that the perpendicular line here is perpendicular to the rake face, okay? So you can say that since alpha, I know that this angle here is alpha, and we have a mathematical property saying that if I have two lines forming an angle alpha, if I do the perpendicular to the first and the perpendicular to the second, I'll obtain the same angle. So you can say that the angle here is alpha, okay? Then you can deduce that theta is simply the difference between big angle alpha and the small big angle phi and the small angle alpha. So theta is equal to alpha to phi minus alpha. If the figure is not clear, I can repeat. Is it clear for you how we got theta equal to phi minus alpha? Okay, so once I got the angle here and I can replace theta by its value, then now I can find the ratio of T0 over Tc. As you will see, the length will be simplified because you can replace T0 by the shear length times sine phi. And you can replace Tc, which is the chip thickness after the cutting operation, which is shear length times cosine phi minus alpha. So LS will be simplified, okay? And then you will get that the ratio is function of the angles phi and alpha, okay? So going back to our document here, we can derive the relation between the thickness ratio and the angle, the rake angle and the shear angle, okay? And also start using this relation by some trigonometrical relations, you can demonstrate. If you want, Anna, for the links I posted, you have the complete demonstration with all trigonometrical rules. But no, you are not responsible of trigonometrical derivation. But if it is interesting for you, you can find all derivations of trigonometrical relations in the links. The links I provide in chapter 17 will be demonstrations of all of these formulas and also some practice problems. And we will do also together some practice problems. So it is good to look at the videos because you will have demonstration of all of these relations plus some problems, some extra problems to do. So if we rearrange just the terms and we use the correct trigonometrical relations, we can come up with the following relation to get the shear angle. So the shear angle is given by r cosine alpha over 1 minus r sine alpha. Okay, and already in the course material we have seen that the shear strain also can be the derived function of phi and alpha. Okay, so you should know that in case I ask for the shear strain, which is the deformation that will be done through the cutting process. It is given by tangent phi minus alpha plus cotangent phi. This formula is in the slides, and also if you are interested in complete derivation, you have complete derivations in the video. Okay, and it's based on the geometry of the chip. So starting from the geometry of the chip, you can demonstrate what is the shear strain. Now we will move to determination of forces in metal cutting. Okay, so forces are essential in this operation because they will lead to deformation, and of course we should have that the tool should be much harder than the work part in order to not have deformation of the tool. So let us consider the forces acting on the chip during orthogonal cutting, and we will see the representation. The forces applied against the chip by the tool can be separated into two mutually perpendicular components: the friction force and the normal force. The friction force F is the frictional force resisting the flow of the chip along the rake face of the tool, while the normal force to friction N is perpendicular to the friction force. And these two components can be used to define the coefficient of friction between the tool and the chip. And here you can see that the friction will play a role in, if you want, so as you can see here in the figure, okay, you have the friction between the tool and the chip is required to perform the operation. Okay, so we have that between the chip and the tool, we have action reaction. So if we consider first the action of the tool on the work force, okay, so we have a force F, which is called, this is the friction force, okay, that will contribute to the operation, and we have the normal force also. Now, by action reaction, the force of the tool on the chip will be equal to the force of the chip on the tool. Okay, and here at the level of the shear plane, we can also demonstrate that we can divide into two components, and we will talk about them now. Okay, so for the action of the tool on the chip, you define friction normal, and the angle between the normal and the resultant force is angle beta. So beta is determined by the ratio. So we can say that tangent of beta is F over N. Okay. And we know that F over N will give us the friction coefficient, because the definition of friction coefficient is that the friction force is equal to the coefficient of friction times the normal force. This is why you can replace here beta by, so in order to calculate beta, all you need to know is the friction coefficient mu. Okay, so mu is defined as the ratio of F over N, and F over N, as we can see in the figure, represents the angle between the resultant force and our normal force. So a tangent of beta is given by the friction coefficient mu. And in addition to the tool forces acting on the chip, there are two force components applied by the workpiece on the chip. So the chip is subjected from one side to the tool action and from the other side to the workpiece action. Okay, and the workpiece action on the chip can be divided into shear force and normal force to shear. So the shear force Fs will be the force that will cause shear deformation. So it will be in the shear plane, while the normal force to shear, Fn, will be perpendicular to the shear force and therefore perpendicular to the shear plane. And based on the shear force, we can define the shear stress, because we know that the shear stress acting along the shear plane that will cause the cutting operation is defined as the shear force over the area of shear. And you will see that the area of shear can be related to the shear angle, to the chip thickness ratio before cutting T0, and to the width stop. So let us do the analysis on the figure here. So you have shear is taking place through this plane, okay? Then the shear force should be parallel to the plane. So this is the shear force, and this is the force normal to the plane. you can consider that the chip is subjected to two opposing forces, one from the tool and one from the workforce. Okay, so this is why we can say that sum of forces acting from the tool on the chip, the resultant here R, will be opposing the resultant R prime, which is due to the action of the workforce. Okay, so here R prime can be divided into shear force and normal force, Fn. And in this case, you can see that the shear force is doing an angle phi with the horizontal. So if you want to calculate the value of the area on which you are applying the shear, okay, this area can be calculated as, so you know that T0, okay, T0 is this distance here. T0 is the perpendicular distance, okay? And we have that the shear plane is equal to this length times W, okay? W is the width, so it's perpendicular to the screen. So in order to find this length can be related, this is LS that we have seen in the previous model. LS can be related to T0 by saying that LS is T0 over sine phi. So this is why you can say that the area of shear over which you have the cutting operation is equal to this length, which is T0 over sine phi. And of course, we multiply by the width. So the shear area is T0 W over sine of phi. Okay. So now, if you got the shear stress, the force, the shear force, then you can calculate the shear stress by doing the shear force over the area of shear. Okay. Now, how to relate our forces? Since we said that the two forces acting on the chip are opposed, so you can say that it is the same magnitude. So R and R prime will have same magnitude and same direction, but opposite sense. Okay, so we can say that R vector is equal to minus R. So vector R is equal to minus R prime. Okay, and this vectorial relation will allow you to relate the forces together. Okay, how to do this? You know that R, because R is equal to R prime. Okay, so for example, then you can say that I can divide R into F and N, or I can divide it into minus Fs and minus Fn. Okay, and this will allow you to write these relations. We will see together how to write them in detail. So first, let's say here, okay, we want to calculate, our purpose is to find, for example, the cutting force and the thrust force. Okay, we want to see to know what is the cutting force Ft and what is the thrust force Ft. Okay, to calculate these forces, this is equal to R prime. Okay, so we can decompose them. So we can say that Fc plus Ft can be also written as Fs plus Fn, and also it is the opposite of R. So from here, we can say that if I decompose, if I want, this is the force F and this is the force N, okay? I can decompose them in several ways. So I can say that if I decompose, for example, each force on these directions, on the cutting direction and the thrust direction, okay? Then I should obtain that, for example, knowing that my force F here, so let me represent it in this way. This is F, okay? This is F. F, I can divide it if I want to work in this frame. I want to work in the frame of the cutting direction and the thrust direction. So it's a frame like this. Consider, so this is the cutting direction. This is the thrust direction. And then I can say that if I want to decompose F in terms of FC and FT, because at the end, okay, you have that the summation of forces is the same whatever you do. So here, if you do from your vectorial relation, R is equal to minus R prime, okay, and R can be written as F plus N. R is equal to F plus N, okay, and R prime can be written as, so it's equal to minus FC plus FT, FC vector plus FT vector, okay. So here, if you decide to decompose, to project FC and FT on F and N direction, what you will obtain? So you know that the resultant component along the parallel line to the rake face, this one is F, okay. So you can say that if I want to project the other forces اللي هن minus FC, so if I take minus FC, it will be like this, and minus FT will be like this. So if I want to represent these forces here, this is minus FC, okay, because F plus N is minus FC minus FT. So this is FC, okay, and this is FT. So let me clear again so that you see it in a clearer way. This is minus FC. This is vector minus FC. Okay. So minus FC vector. And this is minus FT vector. So now I will say that if I want to decompose my these two forces on this direction, I will obtain the component of the force F. Okay. So if you look at the figure, you have that the angle between Ft, the thrust force, and F is alpha. So the projection of Ft on this direction will be Ft cosine alpha. Okay, and it's since we are considering the opposite of minus of Ft and Ft, as you can see, minus Ft projection will be along F. It's positive, and also the projection of minus Fc along F will be positive. This is why it's plus Ft cosine alpha. And since Fc is perpendicular to Ft, so then I multiply by sine alpha. So plus Fc sine alpha. So I can say that this is the relation between Fc and Ft. Now, I will do the same procedure if I decompose now. If I project my vector, my resultant vector, minus r prime, on the normal direction, here, to the perpendicular to the rake face, I should obtain N, okay? So the projection will be, also as you can see here, the projection of minus Fc will be positive, while the projection of minus Ft will be negative. This is why you will have plus Fc cosine alpha. Here it's cosine alpha along N, because the angle here between N, this is N, okay, and this is Fc. So the angle between them is alpha. Why it's alpha? Because you have that this is the horizontal line perpendicular to the vertical, okay, and you have that N is perpendicular to the rake face. So you have these two lines forming alpha. The two perpendicular lines to these lines will also form alpha. So if I project then Fc on N, okay, I will get plus Fc cosine alpha and minus Ft sine alpha. So this will give me the relation of Fn with the cutting and thrust force. Okay, now if I repeat the same procedure, but now for the shear and normal forces, and it's the same idea, because I have two equal forces, then I can decompose the components, any two components, I can project them on any line I want, and now I will choose to decompose on these directions. Fs, and in order to relate with Fs and Fn, I will project the component along Fs line and along Fn line. Now the angle involved will be phi. So if we try to do it, the same procedure, okay? You have the forces you want to express now. Your purpose is to express Fs, Fn, function of Fc and Ft. So now you will project forces Fc and Ft. Instead of projecting on Fn directions, you will project along Fs and Fn. So same procedure. You say that here, I want to determine first, when I want to project the force Fs, okay, is the force Fc and Ft on Fs line. So this is Fs line. I should determine what is the angle between these forces. So also you present, in this case, this is Fc. Here you don't take the opposite because already Fs plus Fn is equal to R prime, not minus R prime. So now you will take Ft like this. So this is Ft. Okay, so you take plus Ft now and plus Fc because Ft plus Fc will give you R prime. Okay, and also Fs plus Fn will give you R prime. Okay, and now from your figure, it's clear that the angle between the shear force and Fc is phi. So this is Fc. Okay, and the angle of Fc with Ft is equal to phi. So its angle with the other direction will be 90 minus phi. Okay, so when you want to project, if you want, in this case, Fc and Ft along Fs line, so this is Fs line, then you have a positive component along along Fs. This is why Fs will be equal to Fc cosine phi, while the tangential the thrust component, if you project it, will have a negative projection, because when you do this projection on